Welcome everyone to the IMP1 World Seminar, which is an online seminar series run by the International Association of Mathematical Physics. Today, we're delighted to have a talk by Aernout van Enter, who's going to tell us about Dyson models. Aernout, take it away.
Okay, thank you very much, and thank you very much for inviting me. I want to tell you some things about one-sided and two-sided aspects, and basically I want to describe three results we obtained in different collaborations with Rodrigo Bezacot from Sao Paulo, Eric Endo in Shanghai, Arnaud Lee in Paris, Roberto Fernandez in Shanghai, and Muxim Mahmoudov and Yevgeny Verbitsky in Leiden. So let's see. Oh, yeah. So basically, there are two kind of interpretations of this one-sided versus two-sided. One is, if you think of space versus time, this is the question of whether Gibbs measures and G measures what the relation is. And this basically means that the one-sided and two-sided is one direction or two directions. Can you describe the measures by the influence from one side or from two sides? And the second part of the talk is about one-sided versus two-sided in the sense of comparing systems on a full line or a half line. And again, if you think of time, it's kind of natural to have an initial condition and look at a half line. In space, that is a bit less natural. But the whole point of the SRB thermodynamic formalism is to consider the map between the dynamical systems and the one-dimensional statistical mechanics point of view. And with this full line versus half line, we have two kind of results. One is about the behavior of metastates for random boundary conditions at low temperature, and the other is some properties of eigenfunctions of transfer operators, and that is at high temperature. So I want first to give an introduction with an overview. Then I want to talk about the Gibbs measure versus G measure issue. And after that, the second part of the talk will be about the two interacting half-lines, the metastates and the transfer operators. And at the end, I will mention some conclusions, and maybe I mention one or two questions we haven't addressed so far. So what I call Dyson models are long-range, one-dimensional Ising models, which are ferromagnetic and have pair interactions. They contain a parameter, which I call alpha, which determines the polynomial decay of the interaction. And this alpha plays a role which is a little bit like a continuous dimension. We have random variables, Ising variables, or for probabilist, Bernoulli variables, sigma I being plus or minus 1. And we have a long-range Hamiltonian, formally for all the sides in the lattice, the one-dimensional lattice. And the interaction has polynomial decay here with the distance to the power minus alpha. This is the parameter which rules everything. And this simulates higher dimension, and varying the decay power between 1 and 2 is like varying the dimension in short-range models. And the advantage for a mathematical physicist or a mathematician is that you can do this in a neat way, in a continuous way. And the slower decay corresponds here to higher dimensions. There are phase transitions possible even in one dimension, although their kind of folklore is the one dimension have no phase transition. This is not true for long-range interactions. At low temperature, there are multiple Gibbs measures with a positive or negative non-zero spontaneous magnetization. And although Dyson didn't invent a model, he proved the first really serious result. He proved that there is a phase transition. It's a phase transition, proving in this way most of a conjecture due to Mark Katz and Colin Thompson. Since then, there have been a number of different proofs, and the proofs we basically use is a contour low temperature expansion technique, which was originated by Fröhlich and Spencer in the alpha S2 case, and afterwards extended by Cassandro, Ferrari, Merola, and Presutti for a larger class of alphas. And since then, there have been some further extensions by Litton and Picot, plus the Marseille thesis by Litton, who is from Chile, and the Delft thesis by Bruno Kimura, who is Brazilian and now in Japan. So if you compare this decay parameter alpha with the dimension of the short-range models, it depends a little bit on the question you ask, what the appropriate correspondence is. If you think about critical behavior, and once you want to ask about mean field critical behavior, this occurs if alpha is less than 3.5, and this corresponds to d larger than 4. And this means that the correspondence is more or less that alpha is like d plus 2 over d. This is the critical analogy. It's suggestive, but it is only approximate, especially if you go below the critical value. Below in terms of dimensions, above in terms of alpha. For surface to volume arguments, there is a different correspondence. Then the alpha corresponds to d plus 1 over d. So it depends a bit the question you ask and the temperature regime you're in, what the answer is. And it's also the case that for no alpha, you can have rigid interfaces in these one-dimensional models. And this is more like 2-dimension, because in all higher dimensions, short-range models, no interfaces. So the reason to look at a lot of these questions comes from the SRB thermodynamic formalism theory. The point of this is to kind of connect dynamical systems, where the dynamics runs in time, and you map this, you code this as a one-dimensional statistical mechanics in a one-dimensional space. So this one-dimensional letter Z can be interpreted as a discrete time or a discrete space. And people have done it with different degrees of complexity. I will talk about the simplest case, where one has just 2 pure values, plus or minus, at each side. So the simplest example, if you think of time, are Markov chains. Markov chains are determined by transition probabilities from time t to time t plus 1. And the conditional probabilities from past to future, they have the Markov property when the future is independent of the past, given, which means conditioned, on the present. And the spatial Markov property, which we know the best from the nearest neighbor Ising model, describes objects which are called Markov fields. In this case, we have conditional probabilities which work from the outside to the inside. And the Markov property says that the outside and the inside are independent, given conditioned on the borders. So in both cases, we have a Markov property. In space, there are a lot of generalizations to higher dimensions. There are also, so both for time and space, you can make things a lot more complicated. We're looking at continuous time and continuous space. I will look at the simple case of everything discrete and everything one dimension. And I want to kind of tell you that even then, there are some things which require a little bit of thinking and some mathematics. So we look at probability measure on the space of 2 symbol sequences. The configuration space consists of infinite sequences of pluses and minuses. And it is a well-known theorem. It is so well known that it even reached Wikipedia. And you can find the scholarly history of it in Gibbs' book, that stationary Markov chains, which means the invariant Markov measures on histories, and nearest neighbor Gibbs measures in dimension 1 are the same mathematical objects. This is a theorem which was first proven in the 70s, shortly after the Gibbs measures were invented by de Bruch and then Vat en Reuel, and the result is due to Braskamp, who did his PhD in Groningen with the same supervisor as I did, but about 10 years earlier, and Spitzer. And the theorem basically says one-sided Markov equals two-sided Markov. You talk about the same thing if you talk about Markov fields or Markov chains. So if we go beyond this Markov property, then the question is it still the case that the sameness remains true if you weaken the Markov property to some other regularity properties? The first attempt is you could look at general ergodic processes, and then the answer is a very convincing no, because in the 70s, Gurevich, Moscow, and Ornstein and Weiss in the West, they constructed examples which were kind of maximally different. They were one-sided random and two-sided deterministic. Dus the one-sided entropy was positive, the two-sided entropy is 0. The one-sided tail, the sigma algebra, is trivial. The two-sided is maximal and contains everything. So what I learned from working in this area is that ergodic theory is a very one-sided theory. All ergodic invariants are one-sided objects. So if people talk about things which are equivalent in ergodic theory, they always look at one-sided objects. So the second attempt is, if it doesn't work for complete generality, here we look at some moderate general cases. And the case I will look, which seemed a natural class, is the continuous or quasi-local ergodic process. So what happens if we change the independent of Markov to a form of weak dependence? If the future is weakly dependent on the past, given a sufficiently long but finite history, or a sufficiently thick but finite border. Are then the insight and what happens far away almost independent? And can we still say here's something about this one-sided versus two-sided question? By this requirement of continuity, we have excluded the Gurevich and Ornstein-Weiss example, because those are not continuous. And this is a type of question which, under different conditions, have been studied by a number of people in a number of papers. And I wrote a series of these papers, of the author of these papers here below. And the continuity property is in the two-sided case for Gibbs measures, that Gibbs measures, they have two-sided continuous conditional probabilities, and they're more or less characterized by those. That means that the mu of the spin at the origin is a continuous function of all the other spins if you try to condition on it, which means you look at all the eta I, both left and right, different from the origin. So conditioned on the rest of the world, the spin of the origin is continuous. It means if you take a sufficiently large environment of the origin and you fix all the spins, then the conditional probability of the spin at the origin depends very weakly on what happens far away. This is a generalization of the notion of a Markov field. And there is in the time version, there is an object which I call G measures, which was introduced by Mike Keen from Delft, but it has been reinvented a number of times by a number of different authors. which means that it has a number of different names. You can find them described as chains with complete connections, as Dublin measures, as SCUM, which is a kind of abbreviation I like, stochastic chains with unbounded memory. People have called them chains of infinite order, uniform martingales, but they're all the same kind of thing. It means that the conditional probability of the spin at the origin, given the past, given the left, is a continuous function of all the spins in the past, all the spins in the left. So this is a one-sided continuity, and it is a generalization of a Markov chain. And if you impose some extra regularity, there are unique G measures, but if you have just continuity, it is possible to find phase transitions. This was first proven in the 90s by Bremsen and Kalikov. There was originally a claim that you always had uniqueness under continuity. The proof of this that it was wrong was shown by Mike Keen 20 years after the fact, and then it took another 20 years to find the first example where they proved the phase transition. So the answer is that you get sameness if you impose extra regularities, then one-sided can equal to two-sided. And this is basically what you want if you want to apply the Sine-Ruel-Bowen theory, the thermodynamic formalism. But without this extra regularity conditions, continuity is not enough. And the kind of, to me, somewhat surprising result is that neither class includes the other. It was known since 2011, due to an example by Fernandez, Gallo, and Maillard, that there's an example of a G measure which was not a Gibbs measure. And recently we found another example, the so-called Schumann projection, which is the one-dimensional restriction of the two-dimensional nearest neighbor Ising model at low temperature. We showed that is not a Gibbs measure, but it is a G measure. The thing which I want to tell you about goes in the other direction, and that was in a way more new because there was no example of this type known. We showed that the Dyson model at low temperature are Gibbs measures, but non-G measures. The two-dimensional conditional, the two-sided conditional probabilities are continuous, the one-sided are not. And I think it is somehow the first example that the two-sided properties look somewhat more random than the one-sided one. So what is the idea which makes our proof work? It means the idea is that you can go from mesoscopic interface localization to entropic repulsion. In a paper by Cassandro, Merola, Picot, and Rozikov, they showed that if you look at the Dyson model at low temperature with the Bruchian boundary conditions, which means you take all minuses to the left of an interval and all pluses to the right of the interval of size n1, then there is a kind of interface point which is around the center, and this interface point has mesoscopic fluctuations. Mesoscopic meaning of order n1 to the alpha over 2, where alpha is this decay parameter. So it is small o of the volume. So it is not macroscopic, but it is large with respect to the lattice distance 1. So this is why it's mesoscopic. And it's mesoscopic as long as alpha is strictly less than 2. And if alpha would be 2, there still is a phase transition, but then the fluctuations are macroscopic. So as long as alpha is strictly less than 2, we have this mesoscopic interface localization. There is an interface in the middle of the interval, but it fluctuates. So now we made the observation that if instead of taking all spins to the left of the interval minus, we take a huge interval of minuses, of some size and 0, depending on the size of the interval, this kind of simulates minus the boundary condition on the left side. So if you take these minus boundary conditions around this minus interval, they are felt on the side to intervals of a size at least n1. So this means that if you take a huge interval of minuses, any interface point on the right at least has a distance n1 from this huge interval. And this means that entropic repulsion from this huge interval occurs. We usually know entropic repulsion from a hard wall in an Ising model. The hard wall is now the frozen interval. It's one dimension, but the size of the wall goes deep into the past, if you want. So we need for this that the size of the interval times the size of the interval to the power 1 minus alpha is small, then the n1 interval doesn't feel much influence from beyond, which means before the huge interval. So in this interval we consider, the huge interval is effectively infinite. Now, if in the interval we study, we place a large alternating interval of size n2, which is small with respect to the n1 interval, to the right of this n0 interval. It's small with respect to n1, but still large with respect to 1. This costs a finite amount of energy. And the reason that it does so is that if you take an alternating interval, you get a double sum of the I plus 1 minus j to the minus alpha minus the whole thing is the one subtracted. This double sum becomes then a single sum with an extra power, and that means that instead of non-summable, you get something summable. So inserting such an interval will in the beginning cost you a finite amount of energy, however big the interval is. So what happens is that due to this cancellation of pluses and minuses, the g function, which describes the dependence on the past, is discontinuous. So what happens is you take here an alternating interval, and you look at the conditional probability given either the alternating interval preceded by minuses, or the alternating interval preceded by pluses. And the conditional expectation of the x remains larger than some epsilon, however big this alternating interval is. And this means precisely non-continuity. Continuity means things are not allowed to depend too much what happens long ago. In this case, if you are preceded by an alternating interval, the dependence doesn't go to 0. So this means that I have a discontinuity point. These discontinuity points are atypical for the measure, so they have measure 0, but they are non-removable. So the measure is not a G measure. Gibbs measures, more or less by construction, they have two-sided continuity points for the conditional probability. So the two-sided conditional probabilities have no discontinuities. So the conclusion of part A, which is in a paper with Bissacott, Endo, and Lani, is that one-sided continuity is different from two-sided continuity, and neither of them implies the other one. Okay, so this is probably a reasonable point if anyone has a question about this.
Yes. So do you say that this happens for any alpha which is less than 2?
Yes, I said our proof worked for some first for some alpha star slightly larger than 1, because of some technical restriction in the Cassandro et al. Paper. Afterwards, by Litten and Picot and Kimura, they extended it. I think the statement is certainly true for all alpha. In a way, it should be more true closer to 1, but the closer you get to 2, the better you can control the contours.
You said the statement is true for any
For
alpha less than
all alpha at low temperatures.
all alpha means any
alpha between 1 and 2. So
okay, between 1 and 2.
strictly less than 2, strictly larger than 1, and temperature low enough.
Okay, so that is is that the condition that you have low temperature phase?
Yes, this is a condition we have in a low temperature phase. In the high temperature phase, in the Debruccian uniqueness regime, there is a theorem by Fernandez and Maillard that the G measures and Gibbs measures coincide. So this is a typical low temperature statement.
Okay.
It's not true. It is not true. Not only not provable, but not even true at high temperature.
Okay, thank you.
Okay, so this was the first part of the talk, and the second part, I'm talking about two-sided Gibbs measures on the whole line versus one-sided Gibbs measures on half line, the half line Z plus, and the kind of first serious observation, although it looks kind of trivial, is that a whole line consists of two half lines, Z plus and Z minus, and these half lines, they can be coupled or decoupled. And if you decouple them, it means that you have a system with free boundary conditions on one side of each half line. These free boundary conditions means this can be your initial point. If you start your final point, so if you consider these two interacting half lines and you want to couple them, the coupling terms is the sum of all the spins to the left, I less than 0, and all the spins on the right, j larger equals 0, times the Dyson coupling term. I will call here the left half line spins etas and the right half line spins sigmas. So coupled versus decoupled means then comparing the Gibbs measures for H and H prime, in which you subtract the coupling term. And sometimes I write the W with this bar in the middle. So formally, if you write the Radon-Nicodim density between the coupled and uncoupled Gibbs measures on the whole line, it is of the form e to the W divided by the expectation of this exponential of W. And this W will be the Gibbs measure or a Gibbs measure for the H or the H prime. In dynamical systems, people talk about the equilibrium measure, which is shift invariant, or the Gibbs measure, which is this free boundary condition measure. So, and then they look at the Radon-Nicodim densities. So what properties do we know of this W? We know first that it is unbounded. If you look at the total interaction energy between the all plus configurations left and right, or the all minus configurations left and right, it is infinite. And this is true for all alpha larger equal 2, and this condition is needed to have a phase transition at low temperatures. Now, if you look at the Gibbs measure, and you look at high temperature, it is not very difficult to compute that mu W is finite for all alpha, probably strictly larger than 1. This is the expected interaction energy, and the same is true if you put this W in the exponent. So it means that at high temperature, the whole line Radon-Nikodym derivative exists in L1, but it is not supposed to be bounded because of this property 1. At criticality or below criticality, the expectation and the Radon-Nikodym derivative, this expectation is 0, which means that the coupled and the uncoupled Gibbs measures outside the high temperature are singular with respect to each other, not absolutely continuous. At high temperature, they are absolutely continuous. At low temperature and criticality, they are not. So the expected coupling energy is finite between two disordered half-lines, infinite otherwise, and otherwise means either ordered or critical. At high temperature, there is another thing. If you fix the sigmas to be plus on the right, and you look and you take only the averages over the etas on the left, then these expressions are finite only when alpha is larger than 3/2 and infinite otherwise. So we take an average over the etas here, and then we take the interaction energy between an ordered and a disordered half-line. So this is a kind of new threshold of the decay power at alpha is 3/2. I say maybe someone else did it, but I haven't found it in the literature. This 3/2 playing this role. That's the interaction energy between an ordered and a disordered half-line moves from finite to infinite at this value. So why are these things true? If you look at the expectation of the W, this is a sum of a pair of sides over i's and j's, and each term at high temperature, each term is at high temperature is of the form order I minus j to the -2 alpha, and the reason being that the correlations decay at the same rate as the interactions do. So the interaction goes like I minus j to the minus alpha. The correlations go also with the same rate. So you square it, you get this I minus j to the -2 alpha. If you sum this over all spins to the left and all spins to the right, you get something finite. If you look at a ground state or at low temperature, then correlations are lower bounded by a constant. Then this double sum is infinite, like I mentioned it. The all plus or the all minus gives something infinite, and you get a divergent sum. And at criticality, the decay is still divergent, which follows from a paper by Lohmann, Gordon-Slade, and Ben Wallace. So why do we find this 3/2? If you look at the eta I as maximally disordered, which means independent and symmetric, which is basically the infinite temperature, then we can write this W as a sum of eta I times a term of size I to the 1 minus alpha. You take one sum, the sum over all the right half-line, and then you get eta I times all the spins at distance eta or larger from the eta I. So such a sum of sides interacting at distance I has a finite variance if alpha is larger than 3/2. Basically, because these eta i's here are random, instead of taking by a sum the 2 minus alpha, you lose here an extra power 1/2, which is why this 3/2. So you get finite variance for alpha larger than 3/2 and infinite variance otherwise. And if things are not IID, but at high temperature, the behavior is similar. You have weak dependence instead of independence, but the work is harder, but the behavior is the same for the same reason. So this property has somehow two quite different consequences. One is something we studied with Eric Endo and Arnaud Lee, which is if you study metastates, we look at low temperature and we look at the Dyson model with random boundary conditions. If you take random boundary conditions, then the finite volume Gibbs measure is not converging. This is called in the spin glass world the chaotic size dependence, and it means that the Gibbs measures keep oscillating between different possible limit points. Although there is no pointwise limits, as a probabilist, people tend to look, is there a weaker form of convergence? And the answer is there can be distributional limits of finite volume Gibbs measures. These things are objects which are measures concentrated on Gibbs measures, and these things are called metastates. And the consequence of our observation is that metastates live on mixed states if alpha is larger than 3.5. In that case, the boundary bias between the plus and minus converges to a finite random variable, and the metastates live on pure states when alpha is less than 3.5. Then the random bias for a plus or a minus like state diverges. So if you look at for a large volume and with random boundary conditions, typically it looks like either a plus or a minus thing with large probability. The probability that it looks like a mixed state goes to 0.
Arnaud,
yeah.
can I ask? So here you're going back to the problem about just a chain. I mean, you are considering to have chains, and so you're talking about coupling them.
Now I say that somehow I use one of the half chains as boundary condition, and the other half chain as the system. So I say I look at the boundary condition being random, which is so disordered, but because I'm at low temperature, in the interval I study, the system looks essentially ordered. So I have to look at the interaction between the disordered boundary condition and the ordered Gibbs states, but the order can be either plus or minus.
And what is the system you're considering? Are you considering a system with two boundaries, or?
Yes, I consider a system with two boundaries, but the sum of the left boundary and the right boundary is a sum of two random things, which again behaves in the same random way.
Okay.
And the kind of, I would say, essential observation is that you have to look at the interaction between an ordered and a disordered large interval half-line. And that changes from finite to infinite at the value alpha is 3.5. If you look at random boundary conditions in higher dimension, you always have this pure states because the boundary diverges. So the square root of the boundary, which is the kind of random boundary energy, also diverges. It diverges slower than the size of the boundary, but it still diverges. So in this pure states, we use a weak local limit theorem, which we in the past we also used when we looked at the nearest neighbor Ising model with random boundary condition, and we need sometimes sparse sequences of increasing intervals to get a neater result. But those in a way are the technical parts in the proof. The idea is more or less what, like I said, you look at the interaction between the disordered boundary condition and the ordered phases. And that changes from mixed to pure as in the support in the metastates at 3.5. The second consequence is looks very different, although the underlying intuition is surprisingly not so different. You look at the eigenfunctions of the Ruel's transfer operator. If you look on a half line and you look at functions f, once you write for your model a one-sided energy function, so you look at all the energy in which the origin is the most left of the term of the energy thing, then you define a transfer operator as follows, the sum of, which is kind of like shifting this thing. And at high temperature, we found that the Radon-Nikodym derivative between the coupled and the decoupled Gibbs measures restricted to the half-line becomes continuous when alpha is larger than 3.5. Remember, it was not continuous, it was not bounded on the whole line, but on the half, if you take the restriction of the half-line, it becomes bounded. And this expression is of interest because this Radon-Nikodym derivative is the eigenfunction of the transfer operator, and the G function of part A can be expressed as a ratio of the eigenfunction and the shifted eigenfunction times some continuous terms. This was this has been studied by Johansson, Öberg, and Poricott in a recent preprint, and by Fernandez, Verbitsky, and Mahmudov, and myself in another preprint which came in the archive a few months ago. So the half-line density is smoother than the whole line density, and the proofs by Johansson and et al. They use random cluster methods and exponential bounds. We use concentration inequalities. Somehow they have some different ranges where they apply, but the results are both of the morally very equivalent. We both get a 3.5. We both get this is a high temperature property. So the conclusion is that one-sided properties and two-sided properties, they can be different. Between one-sided and two-sided continuity, neither implies the other one. And the second half of my talk, I mentioned that the interaction between an ordered and a disordered half-line becomes infinite beyond the threshold, alpha is 3.5, and that has two consequences. At low temperature, you get a different type of metastates, living either on mixed or on pure Gibbs measures, if you consider a Dyson model with random boundary conditions. And at high temperature, we find that we get either a continuous or a discontinuous eigenfunction of the Ruel transfer operator. And in the meantime, we find that it is possible to have continuity of the half-line Radon-Nikodym density, while the whole line density is discontinuous, which is something I also hadn't kind of realized. Maybe it's possible, but to me it came as new and a bit of a surprise. So this is basically what I wanted to tell you. The main papers, there is one paper by Bissacott, Endo, and Leny, and me in communications, mathematical physics. The metastate study, there is a short version in a memorial volume of Vlado Sidrovicius, and the large paper should appear soon, and hopefully within 1 or 2 weeks. The transfer operator paper came last month on the archive, and the other thing I mentioned was this new version of a G measure, which is not a Gibbs measure, with Schlossman, that appeared earlier this year in a memorial volume for Dima Joffe in the Annales Institut pour Henri Poincaré. So this is basically what I wanted to say, and I wanted to thank again the organizers for inviting me. And one thing I haven't thought of seriously, but I was wondering what happens if you look at external fields. You expect the measures to be kind of well behaved, but then you have to kind of do something different with boundary conditions. And I know that on the whole, that physical equivalence of interactions holds, which means that you can have essentially the same interaction if you change boundary conditions or constant, but on a half line, changing a boundary condition can make a huge difference. So it may be that by playing or optimizing on boundary conditions, we can get something, but we haven't done that yet. But that could be a next question. Okay, so this is more or less what I wanted to say, and I'm happy if people ask questions.
Thank you very much for this this very clear and interesting talk. Yes, we have plenty of time for questions. So if anyone in the audience has a question, please feel free to unmute yourself or to raise your hand if you prefer.
Okay, can I ask a question?
Please.
So in the second part, you told us that the behavior coupling between two half lines is sort of
Yes.
related to the transition of metastates.
Yes.
So is this something very special to this Dyson model, or do you expect to see something like this in a much broader context, even in higher
Well,
dimension?
it seems to be fairly one-dimensional, because
Mhm.
the thing is that these random boundary conditions, if alpha is larger than 3/2, remain essentially bounded, and you don't expect that that in a natural form in high dimension. I know there's a mean field example in some kind of Hopfield model due to Christoph Kuhlske, where he found it, but I think it is more normal, more common to get pure states in the support of your meta states. The fact that you can get mixed states are somehow physically always less visible than pure states. So the fact that you can get them is kind of interesting and a surprise, but I think it is probably a bit more special. The common thing to expect would be pure states. It's kind of interesting that you have here an example where you have mixed states, but we use that the maximal interaction with boundary conditions is infinite, and the typical interaction across the boundary is finite. That is kind of unusual.
Okay, thank you.
Are there any other questions?
Mandy, just one question. Can you also consider continuous spins?
Continuous spins, we haven't thought of it, but I would expect actually yes. I mean, the thing is that the proofs, these contour proofs, are typically not really working very well, because to prove the transition in continuous spins, you use reflection positivity and the infrared bounds. You get more or less the same alpha parameters, but things like the Bruchian boundary conditions, random boundary conditions, so all those things immediately collapse if you want to do reflection positivity. So so I would say the results should be the same. The proofs would require a whole lot of work, and I don't immediately see how to do it. But but also if you have continuous spins with a continuous symmetry, you don't really expect this mesoscopic interfaces. It could work if you would do something like anisotropic continuous spin models, but then you should have some more complicated contour models. But the first part, I don't think that would work. The second part, random boundary conditions, that seems more plausible that it would work. And this transfer operator property, but the first part, I kind of doubt if that would work or how that would work.
Yeah, thanks.
Are there any further questions?
Yes. So this is a rather stupid question about the first part. So I think the idea of this mesoscopic domain wall, also the domain wall with huge fluctuation,
Yeah.
it's something rather interesting, and probably it's a kind of idea that we want to convey to usual physicists. But
Yes.
your conclusion is very, very difficult. I cannot say I really understood your conclusion about G measure and so on. So are there any, easier to understand consequences of the existence of this mesoscopic boundary,
Well,
mesoscopic domain walls?
I would say that if you don't want to think too much about the continuity, which is a kind of locality property, I think saying that what we show is deriving entropic repulsion from this mesoscopic localization. See, if you look at the kind of interesting thing in some sense is that it's not true at zero temperature. At zero temperature, there is no reason for the interface to go to the center. So if you take the Brownian boundary conditions, then the reason why the interface would be in the center is of an entropic character. And the fact that the size of the fluctuations is in a way a second part, but the fact that the thing is away from the boundary is entropic. And if you take to infinite half-lines, it's from the infinite half-line. But if you take a sufficiently large interval, and the interval you study is smaller than that, a sufficiently large finite interval is effectively infinite. So you get entropic repulsion from a hard wall, and the hard wall is kind of turned around. Normally, a hard wall is vertical here. The hard wall is in some sense like horizontal. It's lying down, having a large interval of minuses. So I think the intuitive thing is that you have this entropic repulsion following from this mesoscopic localization. The step to get to continuity, it is strict with the alternating interval, which is not very difficult, but probably you have to sit down for a minute and then you see it. But that's probably difficult to see just from the talk. But the intuition that mesoscopic localization can lead to this entropic repulsion, I think is physically kind of reasonable to understand.
Okay, thank you.
Are there any further questions? Okay, very good. I guess that brings this seminar to an end. Thank you very much to all of you for joining, and to Arnoud for the very interesting seminar and the good questions. I hope that all of you will join us in 2 weeks when we'll have a talk by Ronnie Tomulka, who will be talking about thermal equilibration in quantum systems. So thank you for coming.